Hi, my name is Lily Wall, and today I'll be presenting my Physics 2212 Lab 2 project, which focused on lines of charge and the behavior of charged pieces of tape. The purpose of this experiment was to observe how charges interact, estimate the amount of excess charge on a piece of tape, and then model the system computationally to compare theory with experiment. The fundamental principle behind this project comes from Newton's second law, Coulomb's law, and the concept of electric fields. Coulomb's law tells us that the electric force between two charges depends on their magnitudes and the distance between them. In our setup, the tape strips can't just be treated as point charges. The charge is actually distributed along their length, so we model them as uniformly charged rods instead. Here's how the experiment worked. I created U-tape pairs by sticking tape strips together and peeling them apart to generate charge. To test interactions, I observed how two U-tapes behaved near each other, how a charged tape interacted with my hand, and also how it reacted to a charged plastic pen. Finally, I suspended one tape so it could swing freely, brought another tape near it, and measured the separation distance between them. From these tests, I confirmed that both tapes were positively charged. They repelled each other, but were attracted to neutral objects like my hand and to a negatively charged object like the pen. Using the measured separation distance of about 0.008 meters, I balanced the upward electric force against the downward gravitational force. This allowed me to estimate the charge on each tape. By trial and error with the computational model, I found the charge to be about 3.8 times 10 to the negative 8 coulombs. That charge corresponds to the tapes having lost around 2.4 times 10 to the 11th electrons, which is tiny compared to the number of atoms in the tape, but large enough to create a noticeable repulsion. An interesting part of this project was comparing different models. If you model each tape as a single point charge, like we did in Lab 1, you get 3.7 times 10 to the negative 9th coulombs. But the line charge model from this lab gave me nearly 10 times more charge, around 3.8 times 10 to the negative 8th coulombs. The reason is that the point charge model oversimplifies by concentrating all the charge at one spot, which underestimates the true force. The line charge model is closer to reality since it accounts for the full geometry of the tape. Of course, there were possible errors, small inaccuracies in measuring distances, rounding during calculations, or if the tapes weren't perfectly parallel. Also, handling the tapes could cause charge to leak away. These factors could slightly change the charge value we calculated. To wrap up, this project demonstrated how seemingly simple materials like pieces of tape can be used to explore fundamental ideas in electrostatics. By combining careful measurements with computational modeling, we could better understand how distributed charges behave, and why more realistic models like the line charge approach matter when predicting forces and potentials.